Inside a mountain in northern China, there is a cavern the length of 4 football fields, carved more than 100 meters into solid rock, and inside that cavern, 12 enormous turbines spin day and night, moving billions of liters of water up and down between 2 reservoirs, one near the mountain's summit, one at its base. There is no lithium in this system, no cobalt, no battery cells, no chemistry at all. When the grid needs electricity, water simply falls downhill through the turbines. When the grid has too much electricity to use, the same turbines run in reverse and pump the water back up. That is the entire technology. Gravity, water, and a mountain, storing enough electricity to power several million homes for most of a day. This facility is not a concept. It is the single largest energy storage station on Earth, finished at the end of 2024, and it beat the record held by an American plant in Virginia that had stood unchallenged since 1985. And here is the detail that makes it stranger still. China is, at the exact same time, the single largest battery manufacturer on the planet, producing more lithium-ion cells than every other country combined, for electric cars, for home storage, for grid batteries by the thousands. Yet for the single largest, most ambitious energy storage project the country has ever built, the country that dominates battery manufacturing chose not to use a single battery cell at all. This video is about why. How China built the largest storage station on Earth, why the technology inside it is more than a century old and nobody bothered to build one this size before, and why that decision, batteries for some jobs, mountains for others, might say more about the future of energy storage than either technology could on its own. If you like videos about the technology quietly reshaping how the world works, hit like and subscribe so you do not miss what is coming. Let's start with the problem this thing was actually built to solve. Wind and solar power share one enormous, inconvenient trait. They generate electricity on nature's schedule, not on the grid schedule. A solar farm in China's northern provinces can produce a flood of clean power at noon and almost nothing 12 hours later, right as the evening demand spike hits. A wind farm can be spinning flat out at 3 in the morning, when almost nobody actually needs the electricity, and barely turning during a still, humid summer afternoon when every air conditioner in the province switches on at once. When there is more renewable power on the grid than anyone can use, operators are often forced to simply throw it away, a process the industry calls curtailment, switching turbines and panels off, rather than risk overloading the grid with power nobody can absorb in that exact moment. This is not a small theoretical inefficiency. China added a staggering 268 gigawatts of new wind and solar capacity in just the first half of 2025 alone, almost matching the entire amount of wind and solar the United States has ever installed in its history. But building the panels and turbines turned out to be the easy part. National curtailment rates for solar climbed to around 9% in early 2026, and wind curtailment rose past 8%, both roughly doubling year over year. And in resource-rich northwestern provinces like Qinghai and Tibet, curtailment on some days has climbed past 30% of everything those wind and solar farms could theoretically produce. One analysis of the first quarter of 2026 found that China discarded enough clean electricity, simply because the grid could not use it in the moment it was generated, to equal more than France's entire electricity output for the same 3 months. That is not a rounding error. That is one of the largest energy stories in the country, and almost nobody outside the power sector is talking about it. Batteries are one obvious answer, and China is also building those at a staggering pace. But batteries have real limits at grid scale. Lithium-ion cells typically last somewhere between 8 and 15 years before they need replacing. They usually deliver only about 4 to 6 hours of continuous output before running dry, and their component metals, lithium, cobalt, nickel, still have to be mined, refined, and eventually recycled or disposed of. None of that makes batteries useless. It makes them extremely good at one job: fast, precise, short-duration bursts, and less naturally suited to another job entirely, quietly absorbing an entire day's worth of surplus solar power and releasing it again 10 hours later, every single day, for the better part of a century. That second job is exactly what pumped hydro storage was invented to do, and it is nowhere near a new idea. The first pumped storage plants went into operation in Switzerland and Italy in the early 1900s, more than 120 years ago, using the simplest possible principle in physics. Lifting water uphill stores energy. Letting it fall back down releases that same energy again, captured by a turbine on the way past, with very little actually lost in between. It is, in a very real sense, the original battery, just built from water and elevation instead of chemistry, decades before anyone had a practical way to store electricity any other way at meaningful scale. For most of the 20th century, pumped hydro quietly became the backbone of grid-scale electricity storage worldwide, precisely because nobody found anything that could match its combination of massive capacity and multi-decade lifespan. As recently as the mid-2010s, pumped hydro still accounted for the overwhelming majority of all large-scale electricity storage capacity installed anywhere on Earth, batteries included. Big utility projects like Bath County in Virginia opened all the way back in 1985, or Japan's Kanagawa Station, or Snowy Mountains scheme in Australia, all worked on precisely this principle for decades before anyone had heard the phrase grid-scale battery. The idea was never the hard part. Building one bigger and more capable than anyone else ever had was. China picked the town of Fengning, in Hebei province roughly 180 kilometers north of Beijing, for exactly that attempt, and the location was not an accident. Just next door sits Zhangjiakou, home to one of the largest wind and solar power bases in the entire country, with roughly 10 gigawatts of renewable capacity feeding into the regional grid. Construction on the Fengning pumped storage power station began in 2013, with China's state-owned Gejuba Group awarded the main contract the following year, and it took more than a decade to finish. Engineers built two enormous reservoirs, one high on the mountain, one down at its base, each holding somewhere around 40 million cubic meters of usable water, roughly enough to fill 16,000 Olympic swimming pools apiece, and then bored an entire underground complex into the rock between them. 190 separate tunnels and caverns, stretching more than 50 kilometers in total length, centered on a cavern housing the largest underground powerhouse of its kind anywhere in the world, 414 meters long, more than 50 meters tall, carved deep enough into the mountain that the entire structure is essentially invisible from the surface. Drive past Fengning on the surrounding roads and there is nothing to see except a mountain and two reservoirs. The actual machine that makes the whole thing work is buried too deep to notice at all. Inside that powerhouse sit 12 reversible pump turbines, each rated at 300 megawatts, adding up to a combined 3.6 gigawatts, more generating and storing capacity than almost any single power station of any kind on the planet. Two of the 12 are variable speed units, a meaningfully more advanced version of the technology that lets the plant adjust its pumping load on the fly rather than running at one fixed speed, which in practice means it can respond to sudden swings in grid demand far faster than a conventional pumped hydro station ever could. Fengning was also built as the first pumped storage plant in China, connected to what is called a flexible direct current grid, a next-generation transmission system that can route power more precisely across the wider Beijing-Tianjin-Hebei region, itself a world first for a facility of this kind. The first two units came online at the very end of 2021, timed specifically to help power the 2022 Beijing Winter Olympics with clean electricity from the wind and solar farms next door instead of coal. The 12th and final turbine followed in 2024, and with that, Fengning officially became the largest pumped storage power station ever built, surpassing the Bath County plant in Virginia, which had held the record at 3 gigawatts since 1985, for nearly 4 decades. On a typical day, the plant essentially runs on the opposite schedule of a normal power station. Late at night and in the early morning hours, when demand across the region is low, but the Zhangjiakou wind farms next door are often still generating at full tilt, grid operators send that surplus electricity to Fengning, and the plant's turbines switch into pump mode, hauling water from the lower reservoir back up the mountain to the upper one, essentially recharging itself using power that would otherwise have gone to waste. Then, as demand climbs through the morning and into the evening peak, the same units reverse again, releasing water back downhill through the turbines and feeding electricity straight back into the grid exactly when the region needs it most. The mountain, in effect, works a night shift storing power and a day shift delivering it, on a loop that can repeat every single day for decades without a single cell ever needing to be replaced. The numbers behind it, now that it is fully operational, are not projections, they are measured output. At full capacity, all 12 units running together can hold that 3.6 gigawatts of generation for roughly 10.8 hours before the upper reservoir runs dry, meaning the plant can store somewhere in the neighborhood of 40 gigawatt hours of electricity at any given time, enough to power several million typical homes for most of a day. Annually, the station is expected to generate more than 6.6 billion kilowatt hours of electricity, while consuming close to 8.7 billion kilowatt hours to pump the water back uphill in the first place, a round-trip efficiency of roughly 75%, which sounds imperfect until you remember that the alternative being displaced is not perfect either. State Grid, the company that built and operates Fengning, says the plant saves around 480,000 tons of coal and cuts carbon emissions by about 1.2 million tons every single year, simply by letting the region absorb far more of its own wind and solar power instead of burning coal to smooth out the gaps. That single number is worth sitting with for a second. A facility with no fuel, no combustion, and no emissions of its own is functionally acting as a coal plant replacement, purely by making sure clean electricity generated at the wrong time of day does not go to waste. The total project cost roughly 19.24 billion yuan, close to 2.6 billion US dollars, over 11 years of construction, a genuinely enormous upfront bill, financed and built entirely by a state-owned utility willing to think in decades rather than fiscal quarters. Here is the trade-off worth being honest about, because pumped hydro is not simply a better battery in every category. Lithium-ion storage, fresh out of the factory, typically converts somewhere between 88 and 95% of the electricity you put in back out again, noticeably better than pumped hydro's roughly 75 to 82% round-trip efficiency, even with modern variable speed technology like Fengning's. Batteries also react in milliseconds, which matters enormously for split-second grid stability, while a pumped hydro station, however fast for its size, is still fundamentally moving billions of liters of water through tunnels and turbines. What pumped hydro trades that speed and efficiency edge for is durability on a completely different timescale. A well-built pumped hydro station is expected to run for 50 to 100 years, sometimes longer, while a grid-scale lithium battery bank needs its cells replaced every 8 to 15 years, an entire second and often third capital investment over the same stretch of decades. Think of it as the difference between buying a car you plan to replace 3 or 4 times over the next 50 years versus building a bridge once and maintaining it for the rest of the century. Installed cost per kilowatt of capacity for pumped hydro and lithium batteries actually lands in a broadly similar range today, but stretch that cost out across a full century instead of a decade, and pumped hydro's economics start to look very different. This is also exactly why almost nobody builds a pumped hydro station to handle split-second frequency swings, and almost nobody builds a battery bank the size of Fengning to hold 10 hours of a city's electricity supply. Realistic modern grids, including China's, are increasingly built to use both at once. Batteries for the fast, short bursts, mountains full of water for the long, slow, massive ones. Australia is running a version of the same bet right now with its own Snowy 2.0 project, an underground pumped hydro expansion designed to add roughly 2,000 megawatts of capacity and enough storage to power millions of homes for close to a week. Proof that this is not a uniquely Chinese instinct, just one China has executed at a scale nobody else has matched yet. None of this happened by accident or in isolation. China's National Energy Administration has set an explicit national target of 62 gigawatts of pumped hydro storage capacity by 2025 and 120 gigawatts by 2030, and State Grid alone, the utility behind Fengning, already operates a combined 40.6 gigawatts of pumped storage capacity today, with 75 separate facilities either online or under active construction across the country, adding up to 94 gigawatts once every project currently underway is finished. Globally, pumped hydro storage capacity reached roughly 179 gigawatts by 2025, capable of holding around 9,000 gigawatt-hours of electricity in total, and China is now responsible for a growing share of every new gigawatt added to that figure. Fengning is the single largest station in that entire global fleet, but it is explicitly one entry in a list, not a one-off showpiece. It sits inside a broader national strategy of building enormous renewable energy megabases in the country's north and west. More than 250 gigawatts of new wind capacity alone was under construction as of this year, more than the rest of the world combined. And every one of those projects makes storage like Fengning's more valuable, not less. It would be dishonest to end this story sounding like pumped hydro is simply the obvious answer everyone else somehow missed, because the reasons it is not everywhere are real. You cannot build a station like Fengning just anywhere. It requires a very specific kind of terrain, real elevation difference between 2 points close enough together to connect with tunnels, combined with enough available water and geological stability to safely carve a powerhouse the size of a stadium into solid rock. Most of the world's flattest, most populated regions, exactly the places burning the most coal and gas, simply do not have that terrain available nearby. Construction timelines are also brutal by modern energy standards. Fengning took more than a decade from groundbreaking to full commercial operation. Compared with months for a large battery installation, or even a utility-scale solar farm, which matters enormously when a grid needs new storage capacity within the next 2 or 3 years, not the next 10. There are real environmental and social costs too. Flooding and maintaining 2 reservoirs the size of small lakes changes local ecosystems and water tables permanently. Construction on this scale can displace nearby communities, and evaporation from the exposed reservoir surface is a genuine, ongoing water loss in regions that may not have much water to spare in the first place. Permitting a loan for a project like this can take years before a single tunnel is bored, since regulators have to sign off on dam safety, seismic risk, and downstream water rights before construction can even begin. And any of those approvals can stall a project for a decade in places with more contentious water politics than northern Hebei. And even after all of that investment, pumped hydro still cannot do everything. It is a poor fit for the split-second, sub-second frequency corrections a modern grid full of renewables also needs, which is precisely the kind of job lithium batteries are actually built for. Pumped hydro is not a universal fix. It is a powerful tool that only works in the small fraction of the world with the right mountain in the right place, working alongside batteries rather than replacing them outright. Zoom out, and the shape of this story is almost the opposite of the last few breakthroughs you might expect from China's energy sector. There is no new chemistry here, no novel material, nothing patented in the last 5 years. Fengning runs on physics that has been understood and commercially deployed since before the First World War. What China actually did was take a century-old, unglamorous, distinctly unsexy technology, pick exactly the right mountain next to exactly the right wind and solar base, and then commit 11 years and $2.6 billion to building it bigger, more efficient, and more tightly integrated with the grid than anyone else on the planet ever had. No battery chemistry breakthrough required. Just gravity, water, patience, and the willingness to spend a decade drilling through solid rock while everyone else chased something newer. It is also worth noticing what this says about how China is actually approaching its own energy transition, as opposed to how it is often described. The popular version of the story is usually about batteries, about lithium mines, and gigafactories and electric cars. And that story is real too. But the country's single largest storage investment, the one built to solve the hardest and most stubborn part of the renewable energy problem, quietly bet on the oldest technology in the room instead of the newest one. That is not a rejection of batteries. Batteries are still doing the fast, precise, short-duration work no mountain ever could. It is a reminder that the newest available technology is not always the correct tool for every job, and that sometimes the biggest advantage available is not a breakthrough at all, but simply being the one country willing to spend a decade and billions of dollars finishing something everyone else assumed was already too old to matter. If this video showed you a piece of the energy world you had not seen coming, hit like, subscribe, and turn on notifications so you catch the next one. And here's a question for the comments. With a technology this old already proving it can outstore a battery on pure lifespan alone, do you think the next energy storage breakthrough will come from something brand new, or from someone finally scaling up an idea that has been sitting there the whole time?